In this video, we'll be looking at the area between two curves. Another way that you can be asked this question is to find the area of the region described, or the region enclosed. So for this particular example, we're looking at f of x equals 2 minus x squared and g of x equals to x. The first thing I'm always going to do every time I'm given a problem that looks like this, asked to find the area between curves, I'm going to go ahead and look at these equations. I'm going to manipulate them so that there's something that I can graph. Now, by moving this 2 off to the other side and moving this negative x squared in front, this allows me to view this as a quadratic facing down that was shifted up 2 units. So, in that case, I'm going to look at a graph that looks like this. 1, 2, there's the peak of the graph, and it's going to be facing down. Now, the importance of being able to graph these, they don't have to be perfect, but they have to be enough so that I can see where things are looking and how they're going to behave. My next graph is g of x equals to the x function, in which case I'm just going to go ahead and be a linear function centered at the origin. That's going to look like this. Now, the question is if I'm looking at this graph, where is the region enclosed by those two functions? Again, this is f of x and this is g of x. Well, the region enclosed is not going to be this space right here, because you notice it's not bounded entirely. There's a whole set of space down here that's not actually closed. Can't be this section over here. Can't be the section over here. It has to be this entire section right here in the middle. Now, if you have difficulty seeing that, remove the coordinate plane. Rather than drawing the coordinate plane, just draw the images of the graphs that you see to the best of your ability outside of it. And you'll notice very clearly that this section right here is the section that is being encompassed or enclosed. So that's the space that we want to find the area of. Now, the nice part about finding the area between two curves is it's not much different than just finding the area under the curve. Recall, the area under the curve is the integral of f of x dx from some value a to some value b. So if I'm trying to find the area between two curves, the concept is I want this curve to be my upper value, and I want this curve to be my lower value. Now, think of it this way. If I'm trying to cut this space, I'm going to go ahead and use this. If I'm trying to cut this space, I'm going to be cutting down, okay, through those two functions. I'm going to start with this function on top, so f of x in this case comes first, and I'm going to then cut through this one here, which is my lower function. So if I'm looking for the area between two curves, the area between two curves will be from a to b of f of x minus g of x. Now, I'm going to go ahead and change this notation very quickly, because in this particular example, yes, f is on top, g is on the bottom. But I would rather look at it as the top function minus the bottom function. Because if I look at it that way, at the very least, then I'm cutting down vertically. The top function is here, obviously, and the bottom function is here, obviously. So, if that is the case, and I'm looking at this particular setup of the integral, where again, f is on top, g is on the bottom for this particular region, then my integral is going to be the integral of the f function, negative x squared plus 2. I'm going to throw that in parentheses so I don't make any silly mistakes, minus the g function, the function that's on the bottom. Again, I'm going to throw that in parentheses so I don't make any silly mistakes, dx. Now, there's one thing that we don't have here, and that's the bounds. So there are two algebraic things that we're going to have to feel comfortable doing in these problems. Number one is graphing the function. That's step number one. Number two, we have to be able to find out where these two functions are actually intersecting. If we can't find those two values, then we don't know what the bounds are going to be. So keep in mind that this is x equals from a number to another number, but I'm going to go ahead and set these two equations equal to each other. By doing so, x equals negative x squared plus 2, that provides me with the ability to find out where these two graphs intersect. Finding where they intersect is, again, those 2 points right there. So I'm going to go ahead and manipulate this to get it as a quadratic equation equaling to 0. Again, that's how we solve quadratic. So I'm going to add x squared to both sides. I'm going to subtract 2 from both sides. This is going to end up providing me with x squared plus x minus 2 equals to 0. Which, if we're very careful, we'll note, and I'm going to go ahead and draw a line here to try and give myself some space, this should be able to factor into x plus 2, x minus 1 equals to 0. Now, again, remember, this is how we solve any quadratic equation, as we attempt to factor. Then this one here gives me x equals to a negative 2, and this one here gives me x equals to 1. And you'll notice based on my graph here that it looks relatively accurate. This should be at a value of approximately 1, 1, and this one down here should be approximately the value of negative 2, negative 2. And so I'm going to start at the negative 2 value because, again, I want to start at the value that's closest to the negative values of x. And I'm going to cut this, again, I'm going to phrase this in such a way, I'm going to cut this into infinitesimally small rectangles as I go from the x value of negative 2 to the x value of 1. So this right here is the setup of the integral that I need to actually evaluate. So step 3, after again graphing, after step 2, finding the intersection points, and then setting up the integral, is simply just integrate. So I've taken an application problem of this situation and I've changed it into nothing more than a calculus integration problem. So this is equal to the integral of x equals negative 2 to 1. I'm just going to simply rearrange this just a little bit so that it's more clear for me. Again, making it a nice general form of a quadratic. And then I will go ahead and integrate, remembering integration is nothing more than taking the antiderivative first and then plugging in the upper bound minus the lower bound. So I'm going to have negative x to the power of 3 divided by 3 minus x squared divided by 2 plus 2x. Again, I would put a plus c here if there weren't these bounds, but there are bounds, so it's going to be bounded from negative 2 to 1. Again, this one here goes to here, this one here goes to here, this one here goes to here. And now we'll plug in 1 to start, giving me negative 1 cubed divided by 3 minus 1 squared divided by 2 plus 2 times 1. That is me plugging in 1. Minus, I'm subtracting from that, me now plugging in negative 2. Now notice how I'm plugging in negative 2 very carefully with parentheses, and notice how I'm going to go ahead and put a block in front of, again, me starting that term. I have to be very careful about the notation that I use and the way that I use it so that I don't make any silly mathematical mistakes or arithmetic mistakes when I go to simplify this. So, now that I've done this, notice how I didn't put these negatives in parentheses because they are in front of the x cubed, not inside of the x with it cubed. So 1 cubed is 1 divided by 3, so I end up with a negative 1/3 minus a 1/2 plus 2 minus, and then over here very carefully I'm going to go ahead and simplify this. 2 cubed is 8, negative cubed is negative, times the negative is a positive, so that would be 8 over 3. 2 squared is 4, negative squared is positive with a negative, so that's going to stay negative, and it's going to be 4 over 2. Yes, I know that can simplify, and we will simplify it here shortly, minus the 4. At this point, again, if you need to, you can simply type all of these fractions into a calculator and get yourself a number. I'm going to go ahead and simplify it by hand, making sure that I simplify carefully. I'm going to wait on these two fractions just to make sure I don't need to, unless I absolutely need to. Over here, you'll notice I'm going to have 8/3, which I can't simplify down, but I'll distribute the negative to that term there. I will also distribute the negative to this term here, changing this to a positive 2, and the negative to this term here, giving me a positive 4. Now I no longer need any of these parentheses, and I can simplify as I see fit, providing me with a negative 1/3 minus 8/3, giving me a negative 9/3. I'm going to have a negative 1/2, and then I'm going to have positive 2, positive 2, positive 4, which is a positive 8. And now you'll see why I waited to find any common denominators. Negative 3 over 9 is a negative 3 minus a 1/2 plus 8, giving me 5 minus 1/2, or, if you're so inclined, 4.5. Or more appropriately, again, if you'd rather not use a fraction, 9/2. And right there is how you find the area between these two curves.